let's do some example problems with points of inflection. So here we go. Here's a graph of the first derivative. And first question says, what are the critical numbers? Well, remember, critical numbers are when the first derivative is either 0. Oops, that's not one. Where the first derivative is either 0 or undefined. So 0 there, 0 there. So what are those numbers? When x equals 1 and maybe 4.3. And it says determine the x-coordinate of any local minimum point. Well, the minimum point is when my derivative is going to go from a negative value to 0 or undefined to a positive value. So my local min is going to occur at x equals 4.3. Now, on what interval is f both increasing and concave down? Well, it's increasing when the slope is above 0, and it's concave down when my first derivative is decreasing. So where are all those conditions met? They are met right there. So in that region, my first derivative is positive, and it's decreasing, which means it's concave down. So what is that region? Well, that's from -1 to 0. All right, next question. And I'm going to go to another page on that. It says, let there be some function g of x defined here. It wants to find the derivative of f of g of x at x equals 3. Well, we know that the derivative, using the chain rule, is the derivative of g of x times g prime of x. Well, let's do g prime of x over here. G prime of x equals 2x minus 3. And we're trying to find the derivative at 3. So we're trying to find the derivative when x equals 3. So we're talking about f prime of g of 3 times g prime of 3. Well, let's do that work over here. G prime of 3, putting 3 in for x, equals 3, and g of 3 equals, now going into the g function, 3 squared minus 3 times 3 minus 1 equals -1. So we can now simplify this chain rule to f prime of -1 times 3. Well, f prime of -1, if we go to -1, that's right there. So that's roughly 2.2 maybe times 3, which is 6.6. Not bad. Pretty easy to do. The chain rule. This last question, the chain rule question, is a little bit tricky, but once you kind of get the theory, get the idea of what to do, the algebra behind it is not too challenging. Okay. Now here's a graph. It's saying that k is some positive constant, so therefore we know the zeros of my function are at 0 and k. And what I'd like you to do is try to figure this out on your own. Pause the video, and then once you get the answer or get stuck, unpause it and see how you did. So it says find the coordinates of the local minimum point. Well, we know the local minimum point is going to occur right there, and it's going to occur when my derivative is 0. So let's find the derivative. Before we find the derivative, it might be easier for us to expand this function, where k is just a constant. So my derivative is 3x squared minus 2kx. And to find out when it's 0, let's do some factoring. So we can factor out an x. And what we're left is 3x minus 2k. So where are my critical points? My critical points are when x equals 0, or when x equals, solving this for x, that's 2k over 3. And so that's this point right here. That's 2k over 3. So to find out what the minimum point is, now I need to evaluate my function. So my function evaluating it for x equals 2k over 3, so we get 2k over 3 squared minus, well, you know what? Let's just use this function that I found already, the simplified expanded version. So our value, y will equal x cubed, but x is 2k over 3 cubed minus 2k over 3 squared times k. Now let's do a little simplifying. Distributing that cube, we get 8k cubed over 27 minus 4k squared times k, so k cubed over 9. And to get a common denominator, we multiply it by 3 over 3, which is going to give me 12 on the right-hand side. So this simplifies to negative 4k cubed over 27. And what lets us know that it's right is that negative, because we'd expect it to be, a negative y value here. All right, another function. Says, given this function x ln x, find the critical points. So we need to find the derivative. We need to use the product rule here. So it's the derivative of the first times the second plus first times the derivative of the second. And this simplifies to ln x plus 1. And we want to know the critical point is when it's either 0 or undefined. So we want to know, when does ln of x equal negative 1? So to solve this, let's raise both sides. Let's go e to both sides. And we get that x equals e to the negative 1, which is just 1 over e. This says, use the first derivative test to determine if the critical point is a relative max or a relative min. So here's my x value. Here's my derivative. So here we have x less than 1 over e, and x equals 1 over e, and for x greater than 1 over e, at 1 over e, the derivative is 0. When x is greater than 1 over e, if I were to put a number, well, it might help for us to think about what this function looks like. Looks something like this. It's just ln x lifted by 1. So when it's greater than 1, when x is greater than 1 over e, this function is going to be positive. And when it's less than 1 over e, the function's going to be negative. So is it a min or a max? Well, it goes negative, 0, positive. Therefore, it is a min. Now let's verify that result with a second derivative test. And the second derivative test, I think you'll like a lot more. The second derivative test says, well, if my derivative is ln x plus 1, well, my second derivative is going to equal the derivative of ln x, which is 1 over x. And I'm going to evaluate that at my critical point. So y double prime equals 1 over 1 over e. So it just equals e. And that's all we're looking for. Remember, in the second derivative test, is this positive or negative? Well, this is a positive value, which means that we're concave up. Which, because my first derivative equals 0, and my second derivative is greater than 0, the second derivative test implies that this is a, why am I writing min, or max when I know it's a min? And you don't need to remember all of these rules. Like, I mean, don't memorize, well, if the second derivative is greater than 0, therefore it's a min. Just think, if the second derivative is greater than 0, then we're concave up. Know that. That's the thing you should know. And if it's concave up, it's very clear that it's a min. Okay, let's see. The next question says, in the domain 0 to 4, what is the global minimum? Show your analysis. So to find the global minimum, we know that there's a local min. We know that there's a local min when x equals 1 over e. So we need to find out what the value is. So f of 1 over e equals 1 over e times the ln of 1 over e. And, if you have trouble figuring this out, let's actually put this on another page so that we can see it a little bit more clearly. All right, so using our log rules, let's simplify this a little bit more. We have 1 over e times ln of 1 minus ln of e. And we know that ln of 1, is just 0, and ln of e is 1. So this equals negative 1 over e. Yes, you should be able to do that without a calculator. Now that's the minimum value. But what we need to do is we need to see, is it the global minimum? So in order to do that, we need to evaluate f of 0 and f of 4. And going back, just to remember what that function was. It was the function x ln x. So our function here is x ln x, and f of 0 well, let's see. At 0, it should be undefined. Yeah, so f of 0 is undefined because we've got putting 0 in, we'd have 0 times ln of 0, which is undefined. And ln of 0 is undefined. And then at 4, we'd have 4 ln of 4, and that's a pretty big number. Well, not huge, but certainly bigger than a negative number. So the fact that negative 1 over e is the smallest number between the only critical point and my two endpoints, that confirms that this is in fact the global min. Okay, more examples. Last example too. Yeah, last example. So now we're going to have to use the quotient rule. It says find any critical points in the domain x is greater than 0. Well, the critical points, we need to find f prime of x. So f prime of x is low. D high, which is just 1, minus high d low all over low squared. This simplifies. Well, this is minus 2x squared. So this simplifies to minus x squared plus 1 over x squared plus 1 squared. And this is going to be the critical points for x greater than 0. Well, the values of x that would make the numerator 0 would be positive and negative 1. But since x is greater than 0, critical number is just x equals 1. So that's my critical number. That's my critical number. My critical point is when I put 1 in for here. 1 over 1 plus 1 equals 1/2. So my critical point is 1 comma 1/2. Now we want to determine if the critical point is a relative max or a min. So in order to do that, what we do is we take, like we've done a bunch before now, we're going to take x and my derivative. So we're going to look at x less than my critical point, critical number, when x equals 1, and when x is greater than 1. So when x is less than 1, the denominator is always going to be positive. When x is less than 1, that's going to make this negative number less than the positive number. Like for example, if you put 0.5 in, this would be negative 0.25. The whole thing would be 0.75, which is positive. So for x less than 1, it's positive value. When x equals 1, we just found that out, it equals 0. And when x is greater than 1, this is going to be negative and larger in magnitude than the 1. So the whole thing will be negative. So that implies that it's positive, 0, negative, a max. And the last question says, what would be the global minimum on that range? Well, we know, a possibility for the max, a possibility for the maximum value is here. To find the global minimum, we just need to look at the endpoints. So if we look at the endpoints, let's find f of 0. Well, f of 0 is 0 over 1, which is 0. And f of 4 is 4 over 16 plus 1, which is 4/17. So what's our global minimum? Well, our global minimum, it's certainly not this point, which is our max. 0 is smaller than 4/17. So our global minimum is right here. Our global minimum has a value of 0, and it occurs when x equals 0. So that's our minimum point right there. Okay, so that's it. Those are the final examples. It's been a lot, but I wanted you to have a lot of kind of face time with this work.